Well, good afternoon or good morning, wherever you are. Welcome to another Takeo Tuesday. I'm John Barba, along with Rick Mayo from Takeo Comfort Solutions. And we want to thank you for being with us on this fine, beautiful, officially springtime. Are we officially in springtime now? Or we got 5 more days, right, Rick?
Well, like if you go back way back, like that's why I said the Ides of March. Some people would call this New Year's a long time ago. So not quite.
Yeah, I know. I know for Julius Caesar, it was a very bad day.
It was a bad day for yeah,
Today was a bad day for Julius Caesar.
but plenty of people were rejoicing though.
Well, yeah, I suppose. Well, anyway, hey, thanks for being with us, folks. We really do appreciate it. We're excited about today's topic. It's a residential focus, of course, and we're going to talk about sizing, piping, and pumping for indirect water heaters and try to take a little bit of the mystery out of recovery rates and how to figure out what to use and where. The impetus for this presentation actually came from a question a few weeks ago on one of our Takeo After Dark presentations, where one of our guests said, "Hey, you have to size the boiler for the indirect, so you're always going to have an oversized boiler." Says, well, yes and no. I mean, we can certainly size the boiler for the heating load and make the indirect work if we need to. It just depends on how big of a difference there is between your heating load and your domestic hot water load. So we're going to take a look at some of the ways you can work through that today, and then ultimately you can make the best decision of how to size your boiler. Do you size the boiler for the heating load, or do you size the boiler for the DHW load and work backwards? Either way works. It's just good to have the information so you can make the best decision possible. As always, folks, we encourage questions. So please, if you would for me, go to the section on your control panel that says questions/chat and just type in a hi, hello, how are you, and where are you from? Just let's do a little
Coming
bit
in.
of a do a little bit of a roll call. We've got New Jersey represented. We got Chicago, St. Louis, Barrie, Ontario. We got Ohio. Okay,
Even
Wisconsin, New Jersey. Excellent. Look at this, everybody from all over
Oklahoma,
the place. San Diego. All right.
Salt Lake City,
Salt Lake City,
Toronto.
Kitchener, Fairbanks. Welcome, Jerry from Fairbanks.
Yeah.
And we've got Lima, Peru, not to be confused with Lima, Ohio. All right. Very good. Excellent. Well, great. I'm glad we got a nice group of folks with us here. And this is going to be how you ask questions, folks. So when a question comes to you, please type it on in, and I promise you we'll get to every single one of them. We don't hold questions to the end. That's one thing we don't do with Takeo. If you got a question, it's important to you, we want to answer it as quickly as possible. So type in your questions, and we'll watch them as they come up, and maybe every few slides take a quick break, check, and answer what questions that come up. And then we'll stay on as long as you want at the end to answer whatever questions you may have as well. So terrific. Good. I'm glad everybody knows how to do that. And again, chime on in. No, there's no such thing as a bad question. Every question is a good question. And if we know the answer, we'll share it with you. If we don't know the answer, we'll tell you that too. So it's not uncommon that it's very common that I don't know the answer. It's actually fairly rare that Rick doesn't know the answer. So please fire away with your questions. So sizing, piping, and pumping for indirect water heaters. This presentation actually, the original birth of this presentation actually goes back about 25 years to a happenstance a long time ago in a galaxy far away. A company I worked for at the time, we had a guy who was he was the purchasing agent, and he was building a house. And he would come into the factory every day with a set of blueprints under his arm, and he would basically monopolize anybody with ears. He would monopolize their time on getting advice on his heating and cooling system for his house, because that's what we did. And one day he kind of cornered me and was showing me the blueprints and wanted to know about installing radiant heat here, there, and everywhere. And we were looking at the master bathroom, and in the master bathroom, he had a drawing for a great big 2-person tub. And I said, "Hey, that's a cool looking tub. What do you plan to do with that?" And he looked at me with a little twinkle in his eye and says, "You know what I'm going to do with that." And I said, "All right, I don't need to hear any more." And I said, "That's a terrific looking tub. It's nice and big. What do you got for a water heater?" And he said, "Oh, the gas company is giving me for free a 40-gallon water heater." And I looked at him and I said, "Well, what are you going to do with that?" And he goes, "What do you mean, what am I going to do with that?" "I'm going to use it to heat my hot water." He says, "Okay, you can use it to heat your hot water, but then what are you going to do with the tub?" You've got a math problem here, dude. You're not going to be able to fill that tub with a 40-gallon gas water heater. And then he tried to bargain with me. He says, well, what if we're not going to use it all that often, maybe once a month. And he said that how often you use it doesn't make any difference. It's the fact that when you use it, you can't fill it. You're going to have a tub that's maybe a third of the way filled with hot water, and the rest is going to get colder and colder and colder. And by the time you jump in, the mood is gone. Okay, it's just not going to work for you. And he was really struggling with this, and he kept telling me, he says, no, you want me to just spend more money on this? I said, no, I want you to use the tub. So finally, I had to put it into terms that he could understand. I said, when your wife uses the tub and she has to get into the tub dressed like this, you're going to be doing this. Okay, it's just not going to work for you. And then he kind of got it, and we made plans to get a properly sized indirect to go with the rest of his heating system, and he was able to use the tub. But basically what he had, folks, was an arithmetic problem. All right, the tub was bigger than what the water heater could deliver, and that's just basic math at that point. He didn't have enough storage to cover the dump load, which is generally, if you're using a tank type water heater, that's job one. You want to be able to fill a big load with what you have stored. And he certainly didn't have anywhere near enough recovery with a 40-gallon gas water heater. So we got him into an indirect, and the results were much better. What we're going to learn today is how to interpret the data on an info sheet for an indirect water heater. What do all those numbers mean, and where do we get first hour ratings? Where do we get continuous ratings, things like that? We're going to learn the importance of sizing the pipe and the circulator to and from the boiler to the heat exchanger. We're going to learn the importance there as well. Why that's critical, sizing a pump is not just throwing the biggest thing you can find on there and hoping for the best. You want to right size the circulator for maximum performance and maximum efficiency. And then we're going to look at an option or two that might help you get around some of these challenges of boiler sizing, etc. So we're going to take a look at what might be able to work for you. First things first, let's talk about a spec sheet, a typical spec sheet with a for an indirect. And this is we're not endorsing any brand or anything like that. What we're just looking at here is that this is from Superstore, just a company we chose at random to take a look at their spec sheet, because the spec sheets are interesting. And what the spec sheets do is they just give you an awful lot of information. Okay, if we take a look at this, you got the model number, okay, the model number, and the model numbers will tell you the capacity. So SSU 20 is a 20-gallon tank, and SSU 45 is a 45-gallon tank, and so on and so on. So we have that, we have the capacity of the tank. And more importantly, we have the heat exchanger surface area, a very underrated statistic, especially if you're dealing with something that creates hot water, boiler water or water at lower temperatures. You want more square footage of heat exchanger area in order to make those to make the delivery. So the heat exchanger surface area is listed there. Then we have the recommended flow rate and pressure drop. The gallons per minute flow rate that the manufacturer recommends to get the subsequent ratings that you'll see in the next two columns, as well as the pressure drop through that heat exchanger at those flow rates. So for example, if we look at the SSU 45, you see the recommended flow rate is 10 gallons per minute through that heat exchanger. And the pressure drop through that heat exchanger at a flow rate of 10 gallons a minute is 7.9 feet ahead. So that's, again, how we would use that information. And next we have our ratings, okay? If we take a look at the rest of the top chart, you'll see the ratings, both first hour ratings at different water temperatures, meaning the storage water temperature, the temperature of the water you're storing in the tank, 140 and 115. If we have our boiler making 180-degree water, and another column if we have our boiler making 200-degree water. All right, as you can see, the hotter the boiler water, the greater our first hour ratings, obviously. Just it's because we're dealing with hotter water. All right, so there's the top chart. Now the top chart's the happy chart, okay? The top chart tells us we're smart, we're good looking, and people like us, okay? It scenarios you rosily, if you will, okay? All right, it's a nice happy chart, nice happy chart. The bottom chart, however, is where the devil lives, okay? The devil lives in the details. okay, whereas the top chart giveth, okay, again, we take a look at the SSU 45, first hour ratings, 212 gallons, first hour ratings at 140 degree water, stored 292 at 115, okay, that's and then I've got 45 gallons on hand too. I mean, what's not to like? What's not to like about that top chart? Okay, it's looking good, man. This is great. We love this thing. It's the bottom chart, however, that holds you accountable, whereas the top chart giveth, the bottom chart taketh away. And we have to work for this. Okay, we do have to work for this. Because again, let's take a look at the SSU 45. The first half of this thing, or first 3/4 of this thing, is all dimension information, weights, tapping sizes, test pressures, working pressures, blah, blah, blah. It's those last two columns you got to watch out for. All right. So if I'm using a boiler and that boiler is making 180 degree water, the boiler size, in order to get those first hour ratings, that boiler size has to have 141,000 BTU output. At 200 degrees, to get the 200 degree output, the boiler needs to be even bigger at 161,000. So that kind of limits us. Again, let's say if we had a heat load of 70,000 BTUs and I got to put in a boiler that's got an output of 141, virtually all the time, I got a boiler that's a hell of a lot bigger than it needs to be. So I have to reconcile that somehow. Maybe that I have to do that to get the delivery I need, or if I understand how these things work, I might have some options. But that's just what these charts will tell us. So always make sure you check that recommended boiler output. That's the only way you're going to get what they tell you on the first page. Okay.
Hey,
Yes,
John.
sir. Yes, sir.
Not a question yet, but maybe a clarification. You know, we got options up in that the last slide that you had there of tank temperature, right?
Mm-hmm.
Why would somebody want to choose between the two? As far as what is it's a baited question. Folks out there, what does 140 storage tank temperature actually give us as it relates to things that have been talked about within our industry? And just send us something on that. Let me know if you get where I'm going with that. I know John's going to cover some things that do a good job, but something just came to mind. There it is, Legionella, right off the bat. Brian grabbed.
Yep. Yeah, 140 degree storage temperature is going to help you in terms of dealing with taking care of nasty stuff in the tank. Absolutely.
All right. Sorry. Go for it.
Nope. Very good. Very good. What we have here is a math problem. Again, we're talking about just understanding the math behind recovery, understanding the math behind storage, and how we arrived at that 141,000 BTU output. The first thing you have to understand is the math tells us that in any kind of a storage tank, about 75% of that storage tank is actually usable at the temperature the tank is set at. So we had a 45-gallon storage tank, all right? Only 75% of that is usable at 140 degrees. The rest, once we draw that down, the water's gonna be lower in temperature. So why 75%? Well, two reasons. First off, a good portion of that tank is taken up with coil space. A portion of that tank is taken up with coil space. And then the rest is when it is common sense. When you pull hot water out of a tank, it's replaced with, Rick, what's it replaced with?
I have my mic off. I'm sorry. Cold water blending.
Yes.
Cold water blending.
Yes, when you take hot water out, you're putting cold water back in to replace it. You're going to blend the tank down. So really about 75% of that is available for a full temperature dump, if you will. All right. So if we have that 45-gallon tank and we understand that 75% of it is usable, all right, we're going to find that we have available for a full temperature dump about 34 gallons of water in that 45-gallon tank. So 34 gallons of 140 degree water is available to us to do what we want. Now we put a tempering valve on there. Really good idea. That's going to help us out. We mix at the fixture. That's going to help us out as well, because we obviously don't want to be scalding anybody. So figuring the recovery. So that's a portion of that first hour rating, because that first hour rating takes into account what you have available in the tank. The rest comes down to recovery. And recovery is a math problem involving BTUs and GPM. Now, it's not how many BTUs we can deliver with the GPM flow rate like we would figure for a heating zone. What we're trying to figure out is how many gallons per minute recovery can I create with the BTUs available in the boiler. What do I have in the boiler? The BTUs available in the boiler, if we have domestic hot water priority, that's going to dictate my rate of recovery in my tank. So how many gallons per minute can I make with the BTUs that are in fact available? And you knew this was coming. There's a math formula for that, friends, and here it is. If you want to find out your rate of recovery, in gallons per minute, simply divide the DOE boiler output, right? That the DOE rating or the DOE boiler output by the product of 8.33 times 60 times 90. 8.33 is the weight of 1 gallon of water, all right? 1 gallon of water, 8.33. 60, that's the number of minutes in an hour. And 90 is the DOE recommended temperature rise for sizing these things, meaning the water is going to rise 90 degrees. This case comes in at 50, we store it at 140. That's the 90-degree temperature rise that we're talking about. If we were to math that out, it's 44,000 and change. We're going to call it 45,000. All right, just to round up, call it 45,000 and we'll call it good. So in this case, you simply divide the boiler output by 45,000 and that'll get you in the ballpark. Let's take a look. Let's do the math with Homer. So 141,000, which is the recommended output of the boiler for that first hour rating that we saw in the chart, divided by 8.33 times 60 times 90, or 45,000, is going to give us just over 3 gallons per minute worth of recovery. So it's just over 3 gallons per minute worth of recovery. So for 60 full minutes, if I'm in domestic hot water priority for 60 full minutes, I will recover at a rate of just over 3 gallons per minute. We'll call it 3 because we rounded up with the 45,000. We'll call it 3 gallons per minute. What's that over an hour? Well, that's easy math. 3 gallons per minute times 60 minutes in an hour, that's 180 gallons. So I can recover at a rate of 180 gallons for that first hour. Now remember, our first hour rating was what? 232? I think it was, or 212. First hour rating was 212 if we stored at 140. So 180 gallons is my recovery, plus the 34 gallons that I'm storing. That's 214 first hour gallons. The chart said 212. We rounded close enough. That's kind of where that number comes from. 34 gallons stored plus the rate of recovery, 214 first hour gallons. Well, that should make anybody happy. Doesn't matter how old you are, right? If we divide that by 60, all right, that means we can turn on a spigot. We can turn on a faucet and run it at 3.5 gallons per minute for that first hour, and we will not run out of 140-degree water. Now, you don't want the young lad there in that bathtub bathing in 140-degree water. Absolutely not. You're going to temper at the fixture if you do not have a mix valve, and you're going to make sure that you're going to enhance that gallons per minute even more by tempering at the fixture. One of the cool things about most indirects is in normal situations, they're very, very forgiving. You've got a lot of leeway here that you can install stuff and not make a bad mistake, okay, if everything else is done properly. So in this case, if I store at 140 and I temper down, it's very unlikely in normal situations that I will run out of hot water. Now, what if I have 3 showers running at the same time and everybody takes a marathon shower really, really hot? If we're talking 30-minute showers, yeah, you may find that you're going to run down here, maybe more, depending upon the shower and the flow rate. Those are circumstances that you may or may not be able to foresee. But that's, again, normal circumstances. You'll find that in most cases, this is going to be an acceptable result. All right. Now, this is what you get, but again, it's a big if, right? We have a big if here. And what are those ifs? What are the things that have to happen here, folks? Type those in for me and let's see what you got. Rick, I lost my question banner here, so I don't know if you can help me out. What are the big ifs here? What are the 3 things that have to happen in order to get that particular performance out of an indirect. What do you guys think?
Waiting for them to come in.
Waiting for them to come in.
140-degree supply water temperature, says Wayne.
Yep, I got to have 140-degree water temperature coming out of the tank, right? I'm storing at 140. Yep, there's one.
Yep. We got to make sure, Dan Cook says, got to have the piping right and the circulator sizing right. Zoned priority is one response.
Yep, you want to have priority. Yep.
Another one on properly sized circulator, pipe size for the correct distribution, flow rate to the fixture.
Yep.
Yeah.
Well, and again, there's the big thing, that 141,000 BTU boiler.
Yeah.
That's the big one.
That's the source. Yeah.
That's the thing. The 141,000 BTU boiler is the one that's important. All that other stuff's important too. Don't get me wrong. But if I don't have the 141,000 BTUs available at the boiler, this is a pipe dream. Pardon the pun. Yeah, we're not going to get that 3.5 gallons per minute. It's not going to happen. And let's show you. Again, here's the conditions. As we said, you need that 141,000 net at the boiler. The proper boiler piping, meaning the piping to and from the heat exchanger, has to be sized properly for the correct flow rate, and you've got to pick the right circulator. All right, those are the three major conditions that you have in order to get that performance out of the indirect. Let's take a look at them individually. Or let's say, first off, what would happen if we did have a smaller boiler? Say, you know what, 141,000, forget about it. I'm not doing that. All right, I'm sizing the boiler to the load, and I'm going to make the rest work. What will be the net impact on that indirect and its performance? So let's say I'm going to use a smaller boiler. Say it's a 75,000 BTU boiler. The maximum output of this boiler is 75,000. To figure my output, or to figure my recovery rather, I'm going to divide 75,000 by 45,000. Now you can see I've cut my recovery rate nearly in half. I was right about 3 gallons per minute earlier. Now I'm at 1.67. So that's a little less than 50% reduction in recovery. If it's 1.67 gallons per minute times 60 minutes, now my rate of recovery has gone down from 180 gallons in that first hour to 100 gallons. Now I have 100 gallons worth of recovery. I have the 34 gallons stored. That means my first hour rating will be 134 gallons, right? So I've got 134 gallons available. And if I divide that by 60, I'm now at a first hour flow rate of just under 2.25 gallons per minute. And as the man here says, if you run out of hot water mid-shower, you're going to have a bad time, right? This changes things a little bit. But remember, this is 140-degree water. You're not taking a bath or shower in 140-degree water, are you? I hope not. You won't do it twice, that's for sure. So with that 140-degree water stored, I temper either at the tank or at the fixtures. I'm going to expand my usable capacity over that first hour. That rate, that I'm going to have more than 2.25 gallons. Should be fine in normal situations, but there's always those evil situations out there lurking that we have to be cognizant of. Those shower stalls where they've got 15 shower heads coming in every different direction, and they're big enough, you know, for you and 6 of your closest friends to have a shower all at the same time. That's a different animal altogether. You're going to need a big old honking tank there. So it's just the way it goes. So 2.25, just a little under 2.25 gallons per minute in this scenario, again, provided that everything else is sized properly. Okay, provided that everything else is sized properly. Let's go back to pipe sizing here for a second. Now remember, to get that 212 gallons of 140-degree water in, you know, over the first hour, all right, I'm going to need a recommended flow rate of 10 gallons per minute. That means my piping and the circulator between the boiler and the indirect that's piping the boiler water through the coil has to give me 10 gallons per minute of flow rate. At 10 gallons per minute of flow rate and just under 8 feet ahead, what size pipe do I need to run from the boiler to the heat exchanger on the indirect and back again? Let's see if you guys know, what size pipe would you run for 10 gallons a minute? Okay.
We got them coming in. We got a 1 inch. We got 1.25 inches. Keep them coming, folks. 1.5 inches. Somebody's jumping up. There's
All
1.25
right.
inches. There's 1.25 inches. There's 1 inch. There's 1.25 inches. 1.25 inches. One
Yep.
1.25 inches.
You guys are good.
You guys are good.
Yep. I think I think it's Brian Chapman says if it's a short run, 1 inch would be okay, and I tend to agree with him. 1 inch type M copper would be acceptable. I don't think we'd exceed the 4 feet per second rate of velocity there, Rick. A longer run, I think 1.25 inches would be the right number.
I
Now,
agree.
what if? But hey, wait a minute, Rick. Let me ask you this. The tapping on the indirect's only 3/4 inch. You'd have to be a frickin' moron to run 1.25 inch pipe to that. It's just gonna choke down to 3/4 inch. Why on earth would you run 1 inch or 1.25 inch pipe when the hole on the indirect is 3/4 inch?
You want me to comment on that?
I want you to answer that
Okay,
because I
well,
know you know the answer.
think of it just like a control valve. Many times when we have a control valve, let's say it's a three-way mixing valve or a diverting valve on a coil, we might have 1.25 inches running to it for the desired amount of flow. So we want to reduce pressure drop and stuff. But the valve that we're going to might only be 1 inch, and it might only be 3/4 depending on which brand it is, what its CV is. In the case of a heat exchanger, we're just trying to reduce the amount of pressure drop going up to that coil. We've already know what it is at the coil because they gave us that information.
Right, and you can run 10 gallons a minute through that coil, right? But the only way you're going to get 10 gallons a minute through that coil is if you bring 10 gallons a minute to that coil, right?
Yeah, the coil's not worried about maximum velocity erosion or anything like that. In fact, they like high flow because we get better heat transfer that way with a turbulent flow pattern and things like that.
Exactly. So we bring 10 gallons a minute to the heat exchanger. That heat exchanger is going to impart almost 8 feet ahead right at that point. Now we also have to take into account the head loss from the boiler to the heat exchanger and back again when we're sizing our circulator. So let's take a look at that and see how that plays out. All right. Now we're going to look at it from two directions here. I'm going to do the head loss through the heat exchanger and the piping at 10 gallons a minute, but also remember we don't have 141,000 BTUs, right? We only have 75,000 BTUs. That's all we can bring to the heat exchanger. So we're not bringing 141,000, we're bringing 75,000. So that changes the flow and head dynamic considerably going to that heat exchanger. Now, typically, when we design residential hydronics for heat delivery, we design around a delta T, a supply and return delta T, or temperature drop. For fin tube baseboard, for air coils, for radiator, whatever. Let's say we design to a delta T of 20 degrees. The water goes out at 180, comes back at 160, with an average water temperature of 170. With indirects, we typically design to a delta T of 30 degrees. So in this case, the water's going out at 180, coming back at 150. So we design around a wider delta T. So if we do the universal hydronics formula, which states that GPM is equal to BTUH divided by delta T times 500 for 100% water, we'll come up with something close to this. 75,000 BTUs, that's what I have available in the boiler, divided by 30 times 500 or 15,000, I'm going to wind up with a flow rate of 5 gallons per minute. And if I do the math at 5 gallons per minute, that flow rate, that head loss through the coil isn't at, that flow rate is half the recommended flow rate at 141,000, but the pressure drop is 1/4 of that pressure drop. That's just kind of how the math works. So really now I'm looking at a flow rate and a pressure loss through that coil of 5 gallons per minute at 2 feet ahead. It's going to make a difference in circulator sizing as well as pipe sizing. Now again, 5 gallons per minute, we're still on that edge of, do I use 3/4? Do I use 1 inch? Okay, you got to make that call. 1 inch would be better because a little lower pressure drop, but we're dealing with 2 feet ahead through the coil. If you went with 3/4, you'd probably be okay. Would you concur with that, Rick?
Yeah,
Yeah, 3 gallons a minute, 5 gallons a minute, 3/4 inch type M should probably be just fine.
Short runs, we can go up to about 6 gallons a minute on 3/4 inch type M copper. That's all. That's what I'm basing that on. So whatever
Okay.
pipe you're using, look at those specifics.
Very good, very good. All right, let's take a look at what this means for circulator sizing, okay? So it's 5 gallons a minute, 3/4 inch pipe, maybe 1 inch pipe is fine. You want to keep that tank as close as possible with minimal fittings if you can pull that off, if that's how the boiler room lays out. And here's an example. So let's say my supply and return piping from the boiler to the tank and back again is about 40 feet, all right? And that's not counting the fittings. I have to include the fittings in here as well. So if we do this, if we look at, okay, say I've got 16 90s, 8 on the supply, 8 on the return. A 90 is worth about worth about 2.5 feet of straight, properly sized pipe. So I've got 16 90s at 2.5 feet each. That's another 40 feet of equivalent length. All right, so I'm looking at about 80 feet total. To estimate the head loss at the flow rate we're talking about, we're going to multiply our total run, which is the 40 feet of measured length plus the 40 feet of equivalent length with those 90s. I multiply that total length times 0.04. 0.04 represents 4 feet of head loss for every 100 feet of straight, properly sized pipe. 4 feet of head loss for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. So in this case, we're looking at an additional 3.2 feet of head, whichever way we're looking at it, additional 3.2 feet of head through the piping, whether it's 3/4 inch or 1 inch, doesn't matter. It's still going to be roughly the same number. Okay, because we're doing it 5 gallons a minute at 3/4 inch. It'll be lower if I did 5 gallons a minute at 1 inch, most definitely lower. But if I did 10 gallons a minute with 1 inch pipe, I'd be right around 3.2 feet ahead. All righty. So let's say we're going to go with the 3/4 inch pipe and the 75,000 BTU boiler. That's 2 feet ahead through the heat exchanger, plus the additional 3.2 feet ahead through the piping. I've got a total head loss of about 5 feet. So I'm going to be looking for a circulator that can do 5 gallons a minute at 5 feet ahead. 5 gallons a minute, 5 feet ahead. That's what we need with a 75,000 BTU boiler. And that's going to put me, let's see, right about there. Put me right about here. If I was going with 10 gallons a minute at 7.9 feet ahead through that heat exchanger, and I add my 3.2, I'm going to be right up here, 10 gallons a minute at a little over 10 feet ahead. So what you're looking at here, folks, if I'm using a 3-speed circulator like the Takeo 0015, the difference is going to be between setting that circulator at low and setting the circulator at high. All right, getting the flow rate correct is going to maximize your output here. Because Rick, what would happen if I ran 10 gallons a minute at 75,000 BTUs through that heat exchanger? Would that make the system work more efficiently or less efficiently? And would I get more output or less output? I think the rate of recovery would be about the same, would it not?
Well, you get a little bit better heat transfer as we run the water a little faster through the heat exchanger, but negligible. The boiler is what it is. That's all we're going to get out of it. So anyway, that's I think I understood your question right.
Right. Yeah. I mean, if I said, the heck with it, I'm going to run that thing at high speed, and I'll do better. You can't do better than what the boiler can do.
That was my point.
Yeah. The boiler's got 75,000 BTUs available to it. If I set that sucker to high, the only thing that's going to happen is that 30-degree delta T I've designed to is going to be probably 15 at best. And now I'm bringing warmer water back to the boiler. That doesn't necessarily do the boiler any favors either. So if you want to make the whole thing work and work efficiently, size that circulator, as appropriately as you can. So in this case, yeah, set it if it's a 75,000 BTU boiler, and that's the rate of recovery I'm shooting for. Set that thing to low. You'll get that thing to work at its best efficiency rate. So good. So again, caveats galore here, things we have to keep in mind. This is if I'm storing at $1.40 and I'm mixing at the fixture. All right, I'm storing at 140, and I'm going to just mix down with my faucet. All right, that 90-degree delta T, that 90-degree temperature rise is for the dead of winter when the water's 50 degrees coming out the ground. All right. If
Yeah.
it's warmer out, obviously we know when it's warmer out and the ground's not as cold, yeah, that water's going to come out a little warmer. So in the summertime, you'll probably have some better performance. All right. But we got to quantify for the worst, as we always do with with boilers and heating and everything. We got to quantify for the worst case scenario, knowing things will be different as it does get warmer. Now, if you go into places like I saw, we had someone from Fairbanks here. A 50-degree water out of the ground in Fairbanks is a pipe dream, right? You're dealing with what, 35-degree water? This changes everything. All right, this changes everything. Now that with the number we had before, 8.33 times 60 times 90, that changes the math. So it's 8.33 times 60 times
105.
105. Yeah, 100. Yeah, exactly. Because we're dealing with just colder water coming out of the ground. Hey, that's life, man. That's Alaska. And you got to allow for that, and that will change the math here as well. Is that right? And also, your usage varies. Again, you got 3 or 4 people taking showers in 3 or 4 different bathrooms at the same time. Okay. Do you plan around that? I guess a lot of that's going to depend on the customer and the use of the home. Rick, you used to live up in Salt Lake, but if you get out into into Park City and the big ski lodges up there,
For sure.
yeah, you've got the only time those homes are used is when whoever owns them has a gaggle of people up there, for a ski trip, and they all get off the slopes at the same time, and they all want to take a shower at the end of the day at the same time. There's no, they don't pay you for excuses. They pay you for hot water. So now
Yeah.
you're going to have to size around that.
And they would do that, John, with that whole dump in mind. They weren't trying to put, instantaneous or tankless water heaters there. You'd see maybe 3 or 4 119-gallon storage tanks with
Right.
coils or
Right.
tank, and just they took care of it with storage.
Yep. Yep. And if that's the problem you need to solve, that's the way to solve the problem.
That's right.
Exactly. Now, another way of helping an indirect or really any tank kind of outperform itself, all right, kind of give it a little kick in the trousers, is with a tempering valve or a mixing valve. And this is kind of just a little bit of a background on TACO. If you take a look at that valve, that's a very, very, very old TACO valve right there. In fact, the second product TACO ever sold, going back to the 1920s, was a mixing valve, just like this. The first product we ever sold, that when we first got started, was a sidearm water heater. We made actually good sized sidearm water heaters to be tacked onto the side of a boiler to make domestic hot water. They were little indirects. It was a copper coil inside of this big cast iron casing that would be connected to water heaters, and they'd be connected to boilers, and they'd be sidearm water heaters. And they worked like a champ. It really, really worked well. They made a metric crap ton of wicked hot water. I mean, really, really hot water. Hot water to the point that it could get too hot. So the success of that first product, the TACO heater, as it became to be known, led to the second product, the mixing valve. And if you want to know why the company's named TACO, here's your answer. People always say, well, why would you name it after a taco? Everybody says taco. So no, it's not taco, it's TACO. Tacos are for eating, TACO is for heating. That's just the way to remember that. But the reason the company's called what it is that TACO wasn't the original name of our company. The original name of the company was the Thermal Appliance Company. Imagine a big old, cast iron casing sidearm water heater. It's big, and you've got a lot of real estate in that cast iron casing to cast the full name of the company into the side of it. Thermal Appliance Company. The original one is from 1920. You'll see Thermal Appliance Company. Well, the second product, the tempering valve or the mixing valve, is a lot smaller. You don't have the real estate there to cast Thermal Appliance Company into it, so they shortened it. Big T, big A, big C, little o. Now, 1922, 1923, whenever this thing came out, people here in the Northeast had never had a taco before. Unless you lived within a few miles of the Rio Grande, maybe you had never heard of a taco before. Nobody thought to call it, to pronounce it taco. It was just natural to pronounce it taco, and that's how the company got its name. So if you're ever on Jeopardy and the category comes up, now you know, man, now you know. That's why it's called taco. That's why it's called taco. So that's the origin of the mixing valve, okay? You mix hot water and cold water to get mixed water coming out of it, all right? And you can adjust the temperature with the dial on that as shown. And again, this is one of our originals. The net result on a tank is it makes the tank, quote unquote, bigger. It enhances the usable capacity at a mixed temperature. So it's a good thing to put on a tank to help improve its performance, all right? And not only is there one math formula for you to figure this out, there are two, and they're pretty simple. It's addition, subtraction, multiplication, division. You guys got it. It's a two-step process, though. The first step is you want to find out a multiplier, what we call the storage factor, to figure out by how much this thing's going to increase the size of any tank, indirect, tank type water heater, regular, gas or electric, doesn't matter. If you want to find out by how much this will increase the capacity, you do the two stages of math. The first stage is this. In the parentheses, the first set of parentheses, we have T mix minus T ink. T mix, that's the temperature of the mixed water, the water coming out of the mix valve. T mix minus T ink, that's the temperature of the incoming water. Okay, the water going into the cold inlet right here, all right, or the water coming out of the ground. So T mix minus T ink, you do that part first, and then you divide that number by the second number, which is T stored. That's the temperature of the water in the tank minus T ink, or the temperature of the incoming water. So T mix minus T ink divided by T stored minus T ink gives you your storage factor. Now, in your handout section, folks, in your handout section, I've got a couple of things for you. One's the TACO product manual or product catalog that you can download. And we also have the, I have a page that has all these different formulas on there for you. So you can download those at your convenience from your handout section. So first part, storage factor, T mix minus T ink divided by T stored minus T ink gives you your storage factor, all right? Your storage factor. So let's do one. Let's say my mixed water temperature is 112. There's a reason I use 112, and we'll talk about that in a second. 112 is my mixed temperature minus 50. That's the incoming temperature divided by my storage temperature of 140 minus the incoming temperature of 50. So we simplify. 112 minus 50 is 62 divided by 140 minus 50. That's 90. So 62 divided by 90 gives me a storage factor of 0.69. 0.69. How do I use that number? Well, to figure out my estimated mixed capacity of the tank, the mixed capacity of the tank, I'm going to divide the usable capacity of the tank, all right, that storage time minus, times 0.75, the actual usable capacity of that tank divided by the storage factor that we just figured out, that's going to give me the tempered capacity of the tank. So usable capacity divided by storage factor gives me tempered capacity. So our storage factor's 0.69, 0.69. That 45-gallon tank we had before, 75% of that is usable. So I have 34 gallons of usable capacity in that tank divided by 0.69. Now my tempered capacity is almost 50 gallons. What I've done here is I've increased the capacity of the tank, the usable capacity of that tank, by about 50%, okay? I've increased it by about 50% by using that tempering valve. Now, the question you might have is, why did I go 140 to 112? That's going to depend upon the type of mix valve you use. The mix valve we used here is one of many that TACO makes, but this valve has a requirement of incoming temperature versus mixed temperature. it has to be above certain, the way the internals work, there has to be a certain gap between those two. This particular valve has a gap of 27 degrees, meaning you want to set it up so the temperature leaving that valve is 27 degrees lower than the water temperature coming in. We make other valves that will have a minimum recommended gap of 10 degrees and even 5 degrees. The reason you want to be wary of that is so you don't get slugs of hot water combined with slugs of cooler water. If you check the valve that you're using and understand the difference between the valve recommends between incoming water and mixed water, then you'll have a nice consistent delivery of a specific temperature. If I
John.
used yeah, go ahead.
Mike's got a good one here that kind of goes tag teams that response. The two things that we got to think about in mixing valves is what you just mentioned as far as temperature. There's a range, but there's also a GPM. There's a minimum flow requirement to get that accuracy as well. Just like you were talking about the accuracy based on the temperature delta T, right? Mm-hmm. Then you also have to be able to give the valve, pull through the valve a minimum amount of flow to get that same accuracy. Because Mike Larson's saying, hey, how much restriction in GPM does the tempering valve versus not having it have? Would it be wise to oversize it to compensate for the restriction? It's like, well, be careful, because you have to be able to meet that minimum flow requirement of that particular size valve. So anyway, just answer questions as they come.
Right. You're gonna. I mean, if you use a valve that's going to give you X amount of GPM out of it, always check the flow rate out of the valve, right? And you're trying to feed a tub filler that's got twice the capacity. Well, okay, you might find that you're gonna you might wind up with a couple of issues there. So it again, all things to take into account. Absolutely. All righty. Very good. Very good. So in this case, we've made the tank. We've turned basically what we've done here is we've turned a 45-gallon tank into maybe a 55 or 60-gallon tank. We've increased the usable capacity. If we really want to get crazy, we can do something really, really wild. And in this case, what if we were to store at an even higher temperature? Let's say we had a tank that was underperforming, all right, that just for whatever reason, I wasn't getting enough out of this tank, all right? And I want to boost its performance to something that will be acceptable to the customer. I would do two things. I can boost the storage temperature, but combine it with a mix valve, all right? And what we'll see is we can really enhance the capabilities of an indirect if we do both. So again, 112 minus 50 divided by 160 minus 50. Instead of storing at 140, we store at 160. Now my storage factor changes. It's now 0.56. If I divide my 34 gallons of usable capacity by 0.56, now my tempered capacity goes up to 60 gallons. And essentially what that is that's the usable capacity of an 80-gallon tank. So what I have done by increasing my storage temperature and adding a mix valve is I've turned a 45-gallon tank into an 80-gallon tank. Now, would you do that when you're designing right up front? Hey, maybe, okay. A lot of people say, if I'm storing at 160, I'm using more energy. Well, yeah, you are, absolutely. That's why it's a solution to a problem rather than a design intent, I think. If you were, from a design intent right from the get-go, you might want to, design it storing about 140 degree water, but putting in an 80-gallon tank, and then maybe a mix valve and get that 80-gallon tank to think it's a 110-gallon tank. All right. It just depends on your design intent. When you're sitting down to solve a problem, what are you trying to accomplish? If you've got equipment that's there already and you're trying to solve a problem, storing at 160 might be a very good solution. Is it going to cost more? Well, yeah, probably a little bit, but you're still mixing it down. All right. If you are designing a boiler and indirect replacement for an existing package, well, then you have the ability to size the tank for capacity that will meet the needs. It just depends on what you're trying to do at that moment. Is it solving a problem or is it preventing one? Yes, sir.
Ivan's got a statement. System level mixing valves are not recommended as system water lower than 140 can create conditions for Legionella contamination. And what he's speaking of is some codes in certain areas are saying, look, it's not just the water heater we're worried about.
Mhm.
Because you can get Legionella within the piping system when it's not used enough, there's not a velocity, enough velocity, etc. So some areas are recommending that everything behind the wall be 140 and you mix at the fixture. Our pressure balance valves and stuff like that for showers are already taking that into consideration. Scald guard, pressure balance, etc. But now we're talking about putting a little 1070 valve underneath the lavatory. So if we had 140, it would never reach the faucet. And just bringing up a point, you have to check with your local codes what they're recommending, what they're not allowing, etc.
Yeah, and I think a lot of that would be dependent on difference locally between commercial and residential codes too. I could see that being more of an issue commercially where you have point of use tempering valves for that very reason.
Yeah.
Residentially, are there different requirements? I think Ivan, it really depends on and A, where you are, and B, which code we're working with and what the application is. So, but yeah, I think absolutely that's something that definitely has to be taken into account. Now, Ryan has a good
Brian wants to
question.
know if can we
Oh,
say there's a storage temperature that's too high?
a lot of that's, I think anything, personally, sending out 140 to a fixture to me is more than you want to do. At that point, you do need some sort of a tempering valve. I think in terms of too high, you're going to be faced with local codes as well as whatever the manufacturer has for a limit on their storage tank. I know in Massachusetts when I worked with the tools, we had one inspector that would put a meat thermometer under the tub spout to check the to check the temperature of the fluid coming out. And if we weren't within guidelines, we had to go change it. All right. So there are going to be codes that are going to that will limit the delivery temperature. As far as codes limiting your storage temperature, that I'm not aware of. And again, a lot of that's going to depend upon, I think, what the manufacturer's limit. But 160, I don't think is too high. You can't, you got to figure too. The higher the boiler temperature, the hotter the water you can store, right? If your boiler's going up to 180, you can't make more. 180 ain't going to happen in the tank. You're going to have some losses there. So I think that might be the best answer we can give you. Who asked the question? Was that Ryan? Yeah,
Yeah.
I think. Let me know if that answered your question. Ryan. Okay.
A lot of stuff coming in, John. So
Oh, this is good.
you
This is
want to keep
good.
knocking away at it. Richard's making a point. He's saying that the Legionella bacteria doesn't reanimate. Once you kill it, you kill it. The only question is it takes 32 minutes at 140 to kill it. So whatever gets out of the tank and goes out in the piping system might reanimate, meaning they will procreate. And so that's just, think about that too, Richard.
Mhm.
Let's see what else we got. Glass line tanks. He's bringing up a point that not everything's stainless steel, John. That people are still using the good old glass line tanks, and I think at higher temperatures, Brian is claiming that they might not last as long. So
Sure, absolutely. Yeah, again, a lot of that, as we said, a lot of that's going to depend on the tank and what the tank manufacturer recommends. Absolutely, absolutely. I just want to share this with you as our last slide. These are the formulas that are in that download in your handout section. Just some useful formulas that you might find helpful. So you can download this slide at your convenience. And at this point, really, it's open season on questions. So we've got a couple here. Ahmad points out that the code limits the water temperature to 120 at the point of use to prevent scalding. I've seen it lower than that in some jurisdictions, Ahmad, but those are things that are very important to keep in mind. Codes supersede anything we'll tell you. But at the fixture itself, is there a difference between residential and commercial codes? Some cases there are, some cases it's just blanket. So again, always follow your local code. And and he says we store water in the tank at 140 because this is where Legionella will grow. Absolutely, absolutely. And again, that Legionella thing, you want to keep the pipes clean. Mixed valve at the fixtures is a great way to do that.
yeah.
All right. Cool, cool. Any other questions that we kind of skimmed over here? Are we that we missed?
Looking,
And guys, did also just fire away whatever questions you have
yeah,
on
it's
this or any
open,
topic, really. Yeah, open forum time.
open season.
Yeah. Was this useful? Did you find this to be helpful? Give us a little bit of feedback on that. I want to make sure that we hopefully gave you the information that you're looking for, and if it was in fact useful. So give us a little bit of feedback there, and we'll see where we're at, and if and what topics you might want in the future. Oh, here we go. Here's a great question from James Laporte. In the world of heat pumps, we will need a larger storage tank. Yes.
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 Hey,
Yes.
stay tuned for that too.
And stay tuned for that. You might want to show up at Takeo after dark, either tomorrow night or the following Tuesday night. But there's a big old yes there. Heat exchanger surface area. That's one of the reasons we talked about it earlier. Heat exchanger surface area is important because you're dealing with 130, maybe 140 degree water coming from that tank or from that unit. So yeah, to get the recovery and the water temperatures you're looking for, yeah, you really do need a large tank with at least 30 to 35 square feet of surface area on that heat exchanger. And a lot of times as well, electric immersion heaters in that indirect to do that disinfecting that we've talked about, to get that water temperature up to 140 degrees for a certain amount of time.
Yeah.
Absolutely. Yeah.
Yeah. Hey, John, another formula that they were looking for, I thought, was earlier question had to do with the additional mixing that you would get at the tub filler. And that's that two-part blending calculation. We could share that one if they want to know, what they're going to get at actually out the faucet of like a Roman tub filler or something. That's something we could share. It's pretty fairly simple. But,
sure, if you've got it off the top of your head, I think.
yeah, well, let's say that we take the temperature of the hot times the flow of the hot. It's the same brackets that John showed you. Temperature of hot times the flow of the hot, and we're going to add that from the temperature of the cold times the flow of the cold. So that's where like say I got a T and I got water coming in here, water coming in here. It's temperature times gallons per minute. We add those together, divide it by the total GPM when you're done. Okay, so let's say you had 10 gallons a minute total. That would be what you would divide by to come up with the new temperature. Now I've got an example that I was using. It's not John's numbers, but it's the same understanding. If I had 120,
do you have that on a presentation or on a screen? I can share the screen with you, and you can turn it over to you, and then you can.
Let's. Well, I got to switch it. I had it on my other. Screen, so let me pull it up on this computer, and I will do that.
All righty. A visual's worth a million words.
Yeah. I might have passed it. There we go. All right.
Got it?
Okay, yeah, go ahead and give it to me.
All righty.
Show my screen. Boom. Does it show up, John?
Yep, I got it.
All right. All right, let me turn these off. You can still.
Yep, we got you.
Still got it. Okay, so there's the formula, folks, if you want to make that note real quick. So again, let's clarify. This is what's going to happen at the tub. And in my example, I was using a big Roman tub filler, just like John was kind of showing. So if we do that, oh, come on, clicker. All right, so 120 would be hot. Maybe that's what's coming out of the tank, okay, or the mixing valve, because now we're downstream, right? So then we got 8 gallons a minute of that temperature water. So 120 times 8 is 960. Then we take the cold water coming in this, my example was 58 degrees, and times 2 gallons a minute. You take those numbers, you add them together, okay? 960 plus 116 gives you 1076. What was our original GPM? Well, right here, 8 plus 2 is 10. So you take that divided by 10. That tells you I got roughly 107, 108 degree water that's going to be coming out of the tub spout. That's your additional blending or mixing calculation.
Yeah, over 10 minutes. So you got 108 degree water for at least 10 minutes. And then you factor in your storage and your recovery. And how long can you take a 108 degree shower? 108-degree shower is pretty
It's
hot too.
warm.
That's pretty warm. Yeah,
I'm pretty sure my wife takes a 108-degree shower, but
yeah. I'm kind of a baby. If it's 100, 102, 103, I get a little antsy.
yeah. Okay.
All right, let's see. Do you recommend special adapters connecting to stainless steel heat exchangers to prevent galvanic reaction? Is iron and copper okay? Should we avoid galvanized adapters? Generally, in my experience has been that usually the manufacturer will have recommendations. Rick, you were with a company that sold stainless steel indirects, correct? What was their
Yes.
recommendation?
Well, we would see dielectric unions used quite a bit. And the idea is to stop any electrolysis from the metal in the tank, but touching, dissimilar metals and the whole concept of dielectric. But my experience was that that's where you always saw the biggest amount of corrosion. I mean, how many folks online right now? In fact, I lost my questions. When I opened up my screen, I lost my.
I've got it up here.
Okay. Uh, when you open up a dielectric, maybe it's been leaking or maybe it's all crusted up, and you go and look. The portion of that dielectric, we used to use quite a bit of 3/4-inch Mayo dielectrics on the threaded portion, the iron portion, and the inside of that part. Now, copper wouldn't have any issue whatsoever above it, but that nipple, that so to speak, or the nipple and the dielectric itself would be where the most gathering of hard water deposits, the lime, the scale, the deposit, that sort of thing. That's where it would get all choked up. And so there was a time that people just said, hey, I'm just going to screw a female adapter on there, put a regular sweat by sweat union, or if I could, you can actually buy threaded by sweat unions that are all copper or half wrought and half bronze. And that tended to last the longest and have the least amount of issues. Again, I can't speak any more to it than that.
Very good. Mike Larson says dielectric unions always scale up in our area.
Yeah.
So yeah, that's it. So, and Rich McGrath has a little more colorful phrase for that. So sure, there we go. As far as sizing the domestic hot water heater is concerned, do you have any platform where we can get guidance? Different reference gives total different capacity requirements. In terms of that, Ali, that's a good question. I've always sized like an indirect. I've always sized the storage capacity to whatever dump load I have. So for example, the bigger the tub, the bigger the tank. So if I had, so that big 2-person tub that we referenced early on in the presentation, our recommendation to that guy was to get an 80-gallon tank, because I think it was an 80-gallon. Yeah, it was an 85-gallon tank, because he wanted enough hot water to get that tub as full as possible. So we didn't take into account recovery, just said, we're going to dump this load into that tank. And that's how we size them. And Rick, you're nodding your head. That's kind of the common wisdom. Is that, if that's the case? And if anybody else out there has any different ways of doing that, please chime in. But that was an affirmative there, Rick?
Yes.
Okay. Yeah. So, yeah. Size the usable capacity to the dump load, I think, would probably be the best rule to follow. All right.
Now the dump load, it could be that big, 4-person bubble tub, but it don't always think that's going to be the worst, because as John mentioned, if the expectation is they're going up to the ski lodge and they want 15 people to take consecutive showers in 3 different showers, all after each other, then all of a sudden that number's bigger than your bubble tub.
Right.
So
whatever
you got to figure out what the math is and have enough to give it to them. So.
Yeah. And one thing we've learned is you can never have too much hot water. You never ever have too much hot water.
You won't get a complaint anyway.
That's right. No one's going to say, I've tried, I can't run that hot water tank down. You better come here and fix it. You'll never get that call.
It ain't going to happen.
That's it. All righty. And yeah, and it's one of those, usually we always talk about sizing correctly. With water heaters, yeah, bigger sometimes doesn't hurt you, you know, until the propane bill comes. There you go.
Yeah.
Dan makes a point here. 1 point, check the chart of the indirect manufacturer, which shows the minimum BTU that the tank needs to properly perform. And it doesn't matter if you throw more BTUs at the tank. The tank cannot provide more first hour capacity. If you need more first hour capacity, then you need to use a bigger tank to increase the first hour rating. And that comes from straight from the source there, Dan. Thank you for sharing
Yeah,
that.
thanks, Dan. Yeah, heat exchanger really says everything. How much surface area? John made a point of saying that. Surface area is really a limiting factor, or is what gives us really good recovery. So keep that in mind when you're looking at those tanks.
Yeah. As Rick is fond of saying, you can't go lower than low, but you can't go higher than max either.
That's right. Yeah.
As much as you might want to. You can bang that nail as hard as you want. It ain't gonna go any further into the wood. See, I did work with tools. Some people don't want to know. McGrath doesn't want to acknowledge it. I worked with tools, man. I was asked not to after a while, but I worked with tools. All righty. Hey, folks, thank you so much for the gift of your time today. We so much enjoyed being with you. On behalf of Rick and myself, I hope we passed the audition. I just watched that the other day. What a great documentary. Get Back. The Beatles Get Back. Highly recommend it if you dig music. But anyway, do appreciate it. And anytime you guys have any questions, please feel free to reach out to either Rick or myself. You will be receiving tomorrow at noon Eastern or wherever it is your time. You'll be receiving a follow-up email from us that will give you a link to the recording of this presentation, so you can go back and watch it as many times as you wish. Share it if you want to, that's fine as well as a link to download a little certificate of attendance. So if you need that for whatever purposes, that will be available to you as well. And that'll be coming to you tomorrow. And next week, our commercial team will be holding a commercial TACO Tuesday, and then we'll be back 2 weeks after that. So we're looking forward to seeing you guys a little bit further down the road. Have yourself a fantastic week. Enjoy spring as it slowly shows up. Hopefully it's making its presence felt where you are. I'm going to go outside and dance in the sunshine because it's spring. I gotta, you know.
You need some vitamin D.
You need some vitamin D. You know what? There is something to be said for that. Yes, absolutely something to be said for those winter blues, and they're going away.
Yeah.
So terrific. Hey guys, thank you so much, and we will see you all down the road. Have a wonderful, wonderful week. Take care,
See you
everybody.
later. Bye-bye.